All right, we're back. Today is session 2. This is GenAI Simplified. So in the previous notebook, we already learned neural networks at a high level. Today, we're gonna get our hands dirty and build a neuron from scratch. So in today's session, we will understand the exact math behind a single neuron. We will implement a neuron using Python and NumPy, and we will visualize what the neuron does, and we will understand the role of weights and biases. And then we will see how changing weights affects predictions. Today, you will need a little bit of background on Python, on loops and functions, and the concept from the previous session. So a good analogy is a neuron is a decision maker. How so? So let's think about if you should buy this coffee, right? And the coffee has a price, which is $5. It has a size of 16 ounce, and you can see its quality ratings of 0.5 stars. But these factors don't matter equally to you. So let's say the price is very important. We give a weight of 0.5, and the size is somehow important, and the quality is moderate important. So let's have a baseline preference. So let's assume you generally like coffee instead of matcha or other bubble tea, right? And then we just give a baseline of 2 points. So then the calculation becomes the decision score, which is should you buy a coffee or no, becomes the price times the price weight plus size times the size weight plus the quality weight plus your baseline. And we get a score of 11. So this calculation here is exactly how a neuron works, right? So we have inputs, which is price, size, and quality, and we have weights. Weights are how much you care about each factor. And we have a bias, which is your baseline preference. So using all the factors above, we will calculate the output. What is your decision? So just to from math perspective, right? So this is what the formula, if you will, is, right? Really simple, the linear algebra, and then this is the equation. I won't dive into too much details about this. Assume we all have the basics here. So let's dive into the code. First, I will give a random seed. This just tells the function that every time I run the random function, it always give me the same answer, so we can reproduce. So first version would be single input, single weight. So let's say this is my neuron. It's just that simple, one line, right? So I define the simple neuron. We'll take an input value, weight, and the bias as the parameter or argument, and then we will return the neuron output. And here is what it does. So we just use input value times weight plus the bias. That's it. So let's test it. For today's use case, the input is how many hours have you studied for a certain topic, and your weight is the study, how effective your study is, and you have a bias towards a knowledge base. So then we will pass in all these inputs into the function that we just defined and print it out. So let's run that. So you can see that we have inputs, we have weight, we have bias, and we have a predicted test score. So this is a calculation, simple enough. Now let's add a little bit complexity here to try to do this for the multiple inputs. So here, I still define a bias. So my output, I will just set as bias. And then I will loop through all the inputs and weights that I passed in. Right? So these are not a single value. So these are a list of input values. Let's say x1, x2, x3, and then I have weights w1, w2, w3, right? So zip means that we will, just like a zipper, right? You zip these two arrays into, in Python, it's called a tuple. We won't dive into that, but you just know that we can get the input value and the weights from this zip function, and then calculate the output. And then we have a for loop here, so we'll add them one by one. So here we have a student data, right? So this student studies 5 hours per day, and the previous test score is 85, and then he has 7 hours of sleep, right? And then this is the weights that we give it for each factor. So for study, it's 0.3. For the previous score, it's 0.7, and 0.2 is the sleep. For the baseline score, we have -50. So this is a bias, right, as a starting baseline. And then we will pass into the neuron with the loop, and then calculate the predicted score. So let's print that out. So you can see here, we have the input, study hours, previous test score, sleep hours, and this is our predicted score. Will this pass? Okay, we just say yes. So it passes certain threshold. It doesn't matter, right? What matters is the step-by-step calculation. You can see here we start with the bias here, -50, and then we add each loop, and then we get a final result. So next, when we do this loop, right, the calculation is really expensive. You may ask, what if the input has a really long array, right? Well, so NumPy solved this for us. So what it does is called vectorized. Let's dive into that. NumPy has a function called dot product, right? So dot product does all the multiplications and addition just in one go, right? So everything that we just calculated, x1 times w1 plus x2 times w2 blah, you just use this one single phrase. Damn, that's so convenient. And then let's run some actual tests. So we have an input array, we have a weights array, and we pass them in, right? And we pass the bias in, right? We put this in the neuron underscore vectorized, which is this function here, and we print out the outcome. So here I also did the loop version as well, and I did a vector version just to see how much we can improve the efficiency. So you can see here the vectorized neuron output is the same, right? 12.40, and with the speed comparison, you can see the loop version and the vector version. So the vectorized version performs 90 times faster, which is huge important. It's very important for a computer to run, right? Think about, we have so many layers, so many neurons, right? If we can improve them, that's a huge win, right? And also, if you know LLM, you can just think about LLM inside this neurons. It's nothing but just dot product. So let's visualize what the neuron does. So here I have with action. So here, let's walk you through the use case. So we have 2D example, right? We try to predict if someone will like a movie based on the movie type. So the movie can be action movie, or it can be a comedy movie, right? So for this person, he has a preference. So how action movie impact his decision is 0.5, right? He really liked action movie, and he hates a comedy movie. So we put a minus 0.3, and he has a positive baseline towards movies, right? So now we will create a plot. We'll just print it out for visualization. And then this is the exact formula here, right? So X times the weight action, Y times weight of the comedy action plus the bias. Let's run that. The whole purpose of this diagram is to show you what we called decision boundary, right? So what it does is you can see a black dot line here, right? So on the x-axis, we have action level, and then we will just read the movie based on if it's 10, it's a super action, right? Like Bruce Lee, or it's 0, no action, like a romantic movie. And then on the y-axis, we have comedy levels, how hilarious it is. So 10 means it's super funny, 0 means it's 0, right? Nothing. So for this line here, this is called decision boundary, meaning that on the right hand side of the line, that means this person will like the movie. Let's take an example of this dot, right? So if it's action movie 4, action level is 4 and the comedy is 2, yes, based on our weight, he will like the movie, right? But if it's super funny with 0 action here, and then it doesn't like the movie. So you can see we translate our problem into a binary classification problem, right? So let's dive into this decision boundary equation. I won't go too much details about it. I have all the formula here, but you can see a view as so we have a neuron equation. So the output equals W1 times X1 plus W2 times X2 plus the bias, right? So this is what we're being all looking for. So decision boundary is where the output is 0, meaning that the line separating the positive from the negative predictions. So if we have this formula here, right, and if I just move the X from this side of the equation to the left side of the equation, then you will get this formula. So what's important is the weight 1 and weight 2. It controls the slope, which is angle and orientation, right? And the bias here controls the y-intercept, which is the position. So let me show you an example. So here I have a output equation of 0.5 as the W1 and minus 0.3 as the W2, right? And then we want to find when output is 0. So I have this equation equals to 0. And then I move X2 to the left of the equation, right? So these two pictures, they are the same, but this is just to show you, if you know linear algebra, this is how you draw this equation on this X1 and X2 axis, right? So we will see how weights controls the boundary orientation. So let's run this cell. Okay, so you can see here, I have 2 dots, right? So I want to classify them as, you know, the dots belongs to the red part. So this is a good boundary that separates them. But let's say how we change the W's that affects this boundary, right? So in the next one, we have W become changed from 1 to 0, right? And then W2 from 0 to 1. So we can see it actually rotates based on the orientation here, right? And then next one is the same. If the bias is not changed, so the line is not moved, it's just rotating based on the center, right? So similar thing here. When we change the W2 to -1, you can see how we are rotating to this diagonal. Similar here, right? So no matter what you change for W1, W2, as long as you don't change the bias, you are actually changing the slope, right? Changing the slope. So this is another example that we can watch how weights rotate the boundary around that. Right, so I have a couple data points, right? So which the green is the class 1, and then the red is class 2, right? So if I just draw a line here with this weights and the bias, I will have a classification, but the accuracy is only 10%, right? Because on the right-hand side, we classify them as red, which means we only get maybe 1 or 2 points here, right? And then the others are wrong, right? Next, we will change the weights and then rotate the slot. So here you can see this is the boundary, and then we got a 53% accuracy. It's still not great until we reach to this weight, and then we get 100% accuracy. So they are all good boundaries that can achieve a 100% accuracy. That's the point I want to make. So how does it help in the real world scenario, right? Why should I learn this? So a real world example is the email spam classification, right? So you have emails every day, and most of the emails are fine. So how we define spam emails? Let's just say spammers, they tend to send you free stuff, right? They tend to trick you. You want to take advantage of the free products, a lot of free coupons, all the great benefits. So if the email contains the words free, we'll count that word, and then that will become a factor, right? And then also the number of exclamation marks. Sometimes they will put exciting exclamation marks, or surprise, big sale, right? So the spam score that we define here would be the weights, W1 times the count of the free word, and plus W2 times the exclamation marks, plus the bias, right? So similar thing here, we have so here, let's say for average emails has 0.5 free, right, and 1 exclamation mark. For the spam emails, they normally have 4 free mentions and 8 exclamation marks. So next, we will have some data pre-processing cleaning to make sure these values are all non-negative. And we will give weights, right? Some of you might ask, where do we get this weight and biases from, right? So we will dive into that in the upcoming lessons. Normally, we train the neural network to get to the perfect weights and biases. But today, let's just assume we have this already, right? Now, let's just print them out. So you can see here, these purple or dark blue dots, they are legitimate emails, which is good, guys. And these are the spam emails, right? These are the data points with the red triangle. And with the correct weights and biases, we're able to draw a line here so that we are able to identify, these are the spam emails, and these are the correct ones, right? Cool. So let's dive into next. Let's dive into how different weights combinations can create boundaries with the different slops, and how this affects classifications. So here would be another example. Let me just execute it, right? So you can see here with the different weights. So this is something we already covered, but it's just to give you another code example for you to try out. You can see the accuracy, they all achieved 100% accuracy, but when we change the weights, and you can see the slop is changing, right? But we always achieve 100% accuracy. So think about it. Why do we see different accuracy scores for different boundary slopes? Because the optimal decision boundary depends on how your data is distributed, right? So if the data is spread diagonally, a diagonal boundary works the best, right? Similar thing for horizontal. That's good enough about the slopes. Let's talk about biases, right? So why do we need biases? Can we just use weights? Someone might ask. Well, it's a great question. Let's see what is bias from a more intuition perspective, right? So think about your starting a race, and different people, they might start in different positions, right? So if without bias, everyone starts at the same position, but in reality, that's not true. So some runners get a head start, and some of them start behind, right? Or another analogy is the baseline mood, right? If you want to calculate how would you like to see the movie, right? If you wake up in the morning and you find out your mood is neutral, right? Then that's without bias. But can you guarantee every day you wake up with a neutral mode? Probably no, right? So in the morning you might have more positive biases, right? So you will have bias of +3, or pessimistic, you have a -2. Similar thing here for credit score threshold, right? If you have more income, and the loan or credit card is most likely to get approved, so you have a head start, and you have a higher baseline, right? Next, let's talk about biases. So for the insights, the bias shifts the decision boundary without changing its orientation. So it's like moving a line up or down, right? Up, down, or left and right without rotating it. Right? So let's see if we can visualize it. So here we have the same weights, but the bias is different, right? So if we look at here, so the bias is 0, right? So everything is centered here, right? With bias 5, -5, right? So we will move this line down, right? So here we're moving this line down here, right? So this is bias -5, and with the bias is +5, you can see that we move the this line up to number 5 here. You can see we didn't change any orientation, but we just moved the line up and down, or some people say left and right, right? So let's say different bias values. Here, let's compare different bias values. You can see here we have a bias of -3.0. That means, so here we have bias is 0.0 right here, and then because the slope is this way, right? When we have bias -3, the slope actually moved up. And similar thing here, if we have a bias is greater, is 3.0, so the slope is actually moved down, right? And you can see it does affect what we call activated points, right? So which means the classification here. So bias becomes especially critical when we deal with imbalanced data set. So let's say if I click on here, so let's talk about some real world example, right? So I think it's worth to talk about it. So in this real world example, we have healthy patients, right? Which is 95 populations. And it has a score of 2.2. And also we have sick patients, which is 5% of the population, right? So 2.2 means I have a cluster, right? The center point is 2.2, right? And the sick patient, I will draw some data points there, and the center point is 5.5. So let's go down here. You can see this is 2.2, right? So with this center, I draw the couple dots of healthy patients, right? So we actually have 190 points as a purple points here, and we have unhealthy, which is sick patients, which we draw at the center of 5.5, which is this point, right? Around this point, I draw all these dots here. This is our data, right? And then we'll create a grade. This is the decision boundary that we will be calculating. So what's important is the matrix here, right? We have healthy scores and we have sick scores. To visualize it, I actually create a diagram. So here we have healthy patients, right? And we have sick patients. So if the score is less than 0, right? that means it is healthy. Prediction is healthy, right? So within the healthy patients, right, the ground truth is negative, right? We only see positive for sick patients. And then we see what is the Neuron score, right? If the Neuron score is, we predicted the Neuron score is less than 0, right? That means they are true negative. They are healthy, and we identify as healthy, right? So for the healthy patients, if we predict that they are sick, that means the prediction score is greater than 0, right? We call that as a false positive. And with the sick patients, right, if we look at the prediction score, if the score is greater than 0, that means we get the prediction. So they are already sick people, and we classify them as sick people. So everything is good. And if they're sick people, but we somehow misidentify them as not sick, right? We think they're healthy. That means it's a false negative, right? So once we understand the false positives, then we'll calculate some matrix. So these are the matrix, right? We want to calculate accuracy, meaning that we have the true positive and the true negative divided by all the healthy patients and sick patients. So these are the accuracy and sensitivity, which in ML world we call that recall, means the true positives, which is the sick people that we identified as sick, and then divided by the total sick patients. This tells us out of all the sick patients, how many did we catch? And then we have another score matrix to calculate out of all the healthy patients, how many did we correctly identify? And then we print them out. So let's take a look at, so here we have the weights and biases, and then we have a decision boundary here. You can see this is the really poor boundary that we identified everybody as sick people. You can see the overall accuracy is 5%, right? Because the actual healthy people here, and we predicted them as the sick people, the amount is 190, right? All the purple dots that we have identified is sick people. And obviously, we also catch the sick people here, the 10 people, because they are all on the other side of the boundary, right? Yes, this is good because we catch all the sick people, but also it's bad somehow because we misidentify the healthy people. Now we will change the biases with the negative bias. It becomes a lot stricter, right? So the line actually moved up, and this time we achieved accuracy of 26%. So out of all the actual healthy people, we identified 132 people as healthy, which is good, right? And then we misidentified 48 people as sick people, but they are actually healthy people. And for the sick people, yes, we caught all of them. So this is just a demonstration to see how in real world the bias will impact our results. The time due, right? So I also provide a really interactive parameter explorer that you can actually change the weight and the biases here, and then see how different score gets impacted, right? So here I have a bunch of data, right? You can actually change the score to, let's say, minus 1.5, and then you'll see how this slope gets changed. Here we go. It becomes this, right? And then it changed the accuracy, it changed everything. All right, I think that's pretty much it for today's lesson. Let's go to some of the pitfalls, right? Do we need biases? Can we just add another input, like a weight input, and then set the weight always as 1? Well, they are the same. You absolutely can, but in fact, it's mathematically equivalent, right? So let's say you have weights and bias, right? And then you want to do weights, right, here and then times 1. Well, you can do that, but it doesn't mean it's the same thing, right? Can a neuron solve any problem? No. because one single neuron can only create a linear decision boundary. What it cannot solve, if someone asks you, right, your interviewer asks you, the XOR problem is a classic example, right? So meaning that if you have inputs 0, right, you will output 0. You have input 0, 1, you output 1. You have 1, 1, you output 0, right? So why it's not equal to? So if I draw the 3 dots here, right? So they are the classification, right? Red, red. Can you draw a line here? Can you draw a line here to separate them? So the green is on one side and the red is on the other, right? You can't. Give it a try and then let me know if you can. What if all weights are the same? Well, you can do that, but in reality, that's normally not the case, right? So here, yeah, I think we covered this already. Why do we need activation functions? All right, so this is for the next lecture, actually. Sometimes instead of the output number, we want a probability, right? Between 0 and 1. Sometimes we want add some nonlinear functions, let's say curve, right? Sometimes we want to threshold the output, right? If the activate only it's strong enough or the data is big enough. Right? So active function, we'll explain that more in the next lesson. All right, so that's for today's lesson. In today's session, let's do a recap. We covered the neuron formula, right? Which is this. It's a bunch of multiplications and additions plus the biases, right? And then we look at the different components, input, weights, bias, and output. So what the weight does is it controls the slope, right? And what bias does, it controls the position. So what are some limitations? So single neuron, it has to do with everything. It can solve linear problem, but it cannot solve problem like XOR or nonlinear problem, right? So you need multiple neurons for that, and you need an activation function for that. And we did some implementations today as well. So congratulations. I'll catch you next one.